In continuation of my video lectures on the thermodynamics of electrochemical cells, today in lecture 2 I shall discuss the EMF of the cells, how the EMF of these reversible cells could be determined experimentally, and how this EMF of these reversible cells could be connected with this thermodynamical properties of this cell reaction. And before that, I again give some more important comment that the Daniell cell, which is very popular, and also I am discussing this Daniell cells again and again. This Daniell cell is not a true reversible cell or perfectly reversible cells. How it is, why it is not a perfectly reversible cells, I give some reason for that. And this is the Daniell cell. Zinc is partially immersed in zinc sulphate solution, copper is immersed in copper sulphate solutions, and this is the porous plug in order to prevent the free mixing of this zinc sulphate and copper sulphate solutions. Here the EMF of this cell, and this EMF, this cell is connected in opposition with this external battery of variable potential, which is E dash, and variability of this potential is controlled by means of a rheostat, whenever this was negative, this is negative, this is also negative, means these two are connected in opposition. So whenever E equal to E dash, no reaction occurs. It is white, okay, means the driving force and opposing force, they are compensated. But whenever E is greater than E dash, means the cell potential is greater than the potential coming from this external battery, then this one is acting as this galvanic cell, and this left hand side the reaction occurs zinc on plus 2 electron oxidation, and this right hand side electrode copper on reacts with copper ion, takes up the 2 electrons from this electrode and forming this copper reduction. And the sum of these two is zinc plus copper ion, giving you the zinc ion and copper whenever this E is greater than E dash. Means the reaction is in the forward direction, and this reaction is spontaneous reactions, and this spontaneous reactions is giving the electrical energy of this shell. But at the liquid junction, whenever a zinc is dissolved here and copper is removed from this right hand side electrode, some sulphate ion remaining in excess, and the sulphate ion in the right hand side electrode is coming through this porous plug to this left hand side in order to keep each solutions electrically neutral. But whenever this E is less than E dash, means the potential of this external battery is kept higher than the cell potential, then this cell is acting as this electrolytic shell. And in that case, in the right hand side electrode, copper is dissolved to give this copper ion plus 2 electron oxidation, and this left hand side electrode, the zinc ion, is taking up these 2 electrons from this zinc plate and giving this reduction. So net reaction, copper plus zinc ion, giving you the copper ion plus zinc. This reaction is totally reversed. In this way, it is no problem. These electrode reactions are totally reversed. So, but if you consider this liquid junction, then at this liquid junction here this copper zinc is deposited, zinc ion is deposited as this zinc metal atom to this on this surface, and so there is an excess of sulphate ions, and this sulphate ions, and here since copper ion is coming, this one is copper ion is in access in this right hand side electrode. So in this case, this to make this each compartment electrically neutral, each half cell electrically neutral, the sulphate ion will move from left hand side to the right hand side, and this transport through this liquid junction is not being reversed, and this is why it is called not truly reversible cells. But however, still then we consider this one as the reversible cell as very small amount, minute, infinitesimal amount of current is drawn, so the change occurs in this electrode and in this liquid junction is very small, infinitesimally small. So this cell we could declare as almost the reversible cell. Next I am coming how very important term, how the important experiment, how this EMF of this reversible cell could be determined by means of an instrument which is called the potentiometer. You know, there is a difference between the potential difference of these two electrodes and the EMF of this potential difference of these two electrodes of this cell and the EMF of these cells. There is a difference. Whenever the circuit is kept open, means then only the potential difference is equal to the EMF of the cell. So this potential of this cell potential of this Daniell cell or any other reversible cells could not be determined by means of voltmeter. Whenever voltmeter is used, which is usual instrument to determine the potential difference, the voltmeter draws some current in order to record the potential difference of these two electrodes. Whenever the voltmeter draws some current, this reactions is coming up. This reaction is coming up. This transport through the liquid junction also occurs. This one occurs. And whenever the concentration around these electrodes are changed, when this electricity is withdrawn from this cell for recording the potential difference in this voltmeter, there is the EMF of this cell will change. So this is one reason, and another reason is that why the voltmeter is not used. Actually, this E cell EMF of the cell is equal to I into R plus a small r. Whenever the current is drawn from this cell, the internal resistance has to be overcome. This R is the resistance of this voltmeter, and small r is the internal resistance of this cell. and this one equal to IR plus I small r. I is the current strength, and this one R is the resistance of this voltmeter. This one is the potential difference plus IR. So this E cell, due to presence of this internal resistance, this potential, the potential difference determined by this voltmeter is less than E cell. So this is why the voltmeter is not used for determining the EMF of this cells. EMF is found to be less. Besides, whenever this cell is operating, this electricity is drawn, finite electricity, whenever it is drawn from this cell it will no longer becomes this reversible cell, it becomes irreversible. And you know, all the thermodynamic principles could be applied for only in the case of this reversible cells. And however, now the vacuum tube voltmeter, vacuum voltmeter or electronic voltmeter is used, and in this case this R is very high, and I is of 10 to the power minus 5 ampere, and so this term becomes negligibly small in that case. If we use this electronic voltmeter or the vacuum voltmeter. So how we could then determine the potential, cell potential or the EMF of this reversible cells? This is the arrangement. This one is the potentiometer. Potentiometer discovered by Pogendorf. Potentiometer. This is potentiometer. First discovered by Pogendorf, it is the compensation, Pogendorf for compensation potentiometer. How it works? So this is the cell X. This is the cell of unknown EMF, and its EMF is to be determined. Here it is the battery. Some battery is used here, and this battery is having the potential greater than the potential of this X, or this one is the standard cell S. And this one is the thick uniform cross section of this wire, metallic wire of very high resistance, and this battery is again connected with this X, with this cell in opposition. And opposition, this is the galvanometer, this is the key, and the potential of this battery is controlled by means of a rheostat. And this jockey, this is the jockey, and this cell is connected to this potentiometer by means of a DP/dt, double pole throw arrangement. Now it is connected with this cell whose EMF is to be determined. Say at this point P, suppose the potential difference due to this battery is compensated with this EMF of this shell. So this EMF of this shell is equal to the potential difference, potential drop between A and P. And again, next way, this cell is detached, and this DP/dt is connected with this standard cell whose EMF is known to us. Then in that case, this jockey moves, and suppose at this point Q is balancing point, null point, where the galvanometer will not record any current flow, and this AQ, potential difference of this AQ compensates or equals to this EMF of this shell. So actually EX divided by potential of this cell X, unknown cell X, divided by potential of EMF of this standard cell is equal to the potential drop between AP and here divided by potential drop between AQ. The uniform current is passed through this wire, and so this one is equal to resistance of AP and divided by resistance of AQ. When resistance, uniform cross section of this wire, same metal, so resistance actually equal to rho into L by A. This is the formula. Then in this case resistance is proportional to this length, so this will be the length of this AP and divided by the length of this AQ, and you know then EX, EMF of this shell is equal to ES, EMF of this standard cell, into the length of AP divided by length of AQ. So by this way, the current is not drawn, or if drawn, the very small amount of this current is drawn whenever a jockey is moved, and this will give you the EMF of these reversible cells by means of potentiometer. Since current is not drawn, there is no chemical change occurs. Or if it change, then this change you can say very infinitesimal change occurs. AS is the EMF of the standard cell. This is shown the standard cell. Standard very popular is the Weston cadmium cell. This is one has taken Weston cadmium cell, and the cell structure is just like H. This is sold. This is very popular and sold in the market, and this is the H-shape cell, standard cell, and here the left hand side a copper cadmium amalgam is placed here in one limb, which is 12.5%, and 12.5% is found to be good. This percentage as the found that the EMF of this cell remains fixed within 10 to 15% of this cadmium amalgam solution. So 10 to 15, the average value have been taken 12.5%. And this one, some cadmium sulphate crystals, cadmium sulphate 8/3 water solid have been taken, kept above this cadmium amalgam. In this case, in the right hand side, it is the mercury liquid is placed in this right hand side limb, and above this one, the paste of mercury and mercurous sulphate have been kept here, and mercury is added to this mercurous sulphate in order to prevent this mercurous ion to convert the mercury ion. Due to disproportionation reactions, mercury plus to this proportional reactions, it gives this again mercurous ion. So in order to prevent the conversions of this mercury sulphate in any way to this mercuric sulphate, this mercury is also added, and by means of disproportionation reactions, this one is controlled. And this above of these two limb, it is saturated solutions of cadmium sulphate. Saturated cadmium sulphate, and since the cadmium sulphate remains here, and so this solution remains always saturated. Here the platinum wire is fixed up. Here also platinum wire fixed up. This is platinum and this is platinum. They are the connecting these electrodes, and this is negative electrode and this is the positive electrode. If we consider these reactions, then cadmium reacts with sulfate ions, cadmium amalgam reacts with sulfate ions and giving the cadmium sulfate plus 2E oxidation. And right hand side there will be a reduction. Mercurous sulfate takes up 2 electrons here from this platinum and gives this 2 mercury liquid and sulfate ions. This is the reduction. If we add this 2, we shall get this net cell reaction, cadmium plus mercurous sulfate, giving you the cadmium sulfate plus twice mercury liquid. So this EMF, this is taken as the standard. Why it is standard? This is very stable. It is stable. Its durability is very high. It remains for a long time with a constant EMF, and the temperature coefficient of this EMF. Temperature coefficient of this EMF for this standard cell is very low. Besides that, this EMF of this standard cell is reproducible. Reproducible means if we do repeated use of this cell, then in every case this cell will give this constant or fixed EMF, and EMF at this temperature T is equal to 1.01830 minus 4.06 into 10 to the minus 5 into T minus 20. Means it is the potential. So whenever the temperature is temperature is 20 degrees centigrade, the potential or EMF of this cell is 1.01830, and the temperature coefficient of this EMF is also very low, minus 4.06 into 10 to the minus 5. This is all about the determination of this EMF of a reversible cell by means of potentiometer. Now I shall try to discuss how this EMF of this cell could be connected with this thermodynamical properties of this cell reactions. So let us see in this next phase. Already I have told in my last lecture the spontaneous reactions could only be used. Spontaneous and also the ionic reactions could be used in the formation of these reversible cells. And you know, whenever the reaction occurs spontaneously, its free energy is decreased whenever conducted at constant temperature and pressure. And from this thermodynamics, this reversible thermodynamics could be applied safely for the reversible cells. And so this free energy decrease in free energy at constant temperature and pressure is equal to the non-mechanical work. Non-mechanical work means del G Tp is equal to minus W non-mechanical. Non-mechanical means non-mechanical work, the magnitude of this non-mechanical work done by the system is equal to this minus del GTP. So electrical work is non-mechanical work, and if for example say zinc plus copper plus 2, and in case of Daniell cell zinc plus 2 plus copper, but this reaction, whenever this reaction will go completion, actually 2 gram equivalent 2 gram equivalent chemical change occurs. 2 gram equivalent chemical change occurs for these reactions. If in some other reactions maybe 1 gram equivalent, 2 gram equivalent, 3 gram equivalent chemical change may occur for the cell reactions. So this non-mechanical work equal to minus, and this NF, this is the amount of electricity, F is the Farad, 96,500 coulomb. So this one is the amount of electricity drawn from the shell, and this potential into this E cell, EMF of this reversible cell. So this is the amount of non-mechanical work done by the shell, and this one equal to this. The T and temperature, pressure constant. This is already implied, and so we write delta G equal to minus NF into E shell. This is very actually, this delta G, the free energy change of the cell reactions or the reactions occurring in the shell. This reaction is very important. Actually, this is the thermodynamics. This obtained in thermodynamical chapter, thermodynamics, and this one is electrochemistry. So whenever we try to jump or find the relations between the thermodynamics and electrochemistry, we have to use these relations, these relations, and so this relation makes a actually bridge between the two chapters, thermodynamics and electrochemistry. Whenever we try to connect this electrochemistry with thermodynamics, we must have to use this one. And you know this from this shell, it is you can see this E cell equal to minus del G divided by L. And since del G is extensive property, this is the extensive property, and this N is also the extensive property. So the ratio of these two extensive property, it becomes the intensive property. So EMF of this shell is an intensive property. Means EMF of this cell does not depend on the size of these cells. Say you know that lead storage cells, sometimes the 12 volt, suppose 6 cells are connected in series to give this 12 volt, and whenever this lead storage battery is used for this for the emergency light, this is very small, and same lead storage cell when used in bus, truck or inverter, it is a big size. So whatever may be the size, its potential is always same, and it is the intensive property. And then another thing is that if this is the cell reaction written stoichiometrically, if we change the stoichiometric equation, suppose it is 2 means 2 gram moles of zinc reacts with 2 gram ounce of this copper, giving you 2 gram ounce of zinc and 2 mole of this copper. Still then this E cell will not change. Another thermodynamic property, say del S entropy change of this cell reaction, and this is equal to minus del G divided by del T at a constant pressure. And you know we have these relations. So if we put here, then this will give you this NF into the E cell divided by del T at a constant pressure. So if we can determine this temperature coefficient of this E cell, and N is the number of gram equivalent change, then F is the Faraday, then delta S could also be determined. is the entropy change of these reactions. So these this one and this one could be determined very simply, and this is very easily calculated. Suppose at 30 degree centigrade, suppose EMF of this cell is E1 determined by means of potentiometer, and 20 degrees centigrade it is suppose E1, then del E cell by del T at constant pressure equal to simply E2 minus E1 divided by 10, and it is a volt part at Kelvin inverse. Another thing is that delta H, another thermodynamical properties, del H equal to or del G equal to del H minus T del S, and so del H, it is the enthalpy change of this cell reactions, equal to delta G plus T delta S. If we put here delta S and delta G here, then it will give you this NF and T into del E cell by del T minus E cell. So this by this fashion, delta H or the enthalpy of these reactions, or you can say the heat of reaction at constant pressure, would also be determined. And these values obtained from this determination of this cell potential will give you the very accurate one. So this is all about the relations between thermodynamical properties of the cell reactions with this EMF of the cells, and this is the property. Only we shall determine this E cell for the whole chapter, and now we connect this E cell with other thermodynamical properties, physical properties of these electrolytic solutions, and we could get the value of these physical properties also. So thank you all for watching this video. I am very much happy to see that a good number of viewers are seeing this video lectures, and I hope again the number of viewers will increase, number of subscribers will increase. So I request you all to subscribe and inspire me to do more video lectures. So thank you all.